mention that henceforth that only link that I posted in your, I sent you an email, all of you. So only the link that is given there, please use that for future classes. And I'm going to delete all other links that we have. On the calendar request, I'm going to delete. It was a complete mess, but I can't help otherwise. Okay. There is another issue because the board that I got for writing typically, I'm talking from office and I'm shocked to see that the cable is not, I've forgotten it at home. So I can't use my pen, my stylus. So I'm going to try to use the mouse, which is probably pretty disastrous, but that is the only way out. Otherwise, I have to drop the class, which I don't want to. So anyway, today what we want to start, and this is actually something which I would have asked had we done this directly. I mean, if this were a face-to-face class, I would have ensured that we would have done this. I would have had you guys mostly solve everything, but since there is a problem, I will try to do the maths, and that is going to be a problem because, as I said, I don't have my stylus. Anyway, so what we do today is, as I said, just let us share my screen. Let me share my screen. Yeah, can you see the whiteboard? Whiteboard, right? So this is basic. The course contents are essentially going to revolve around this piece of this part of this apparatus, trapping a small particle, a very small sized particle, uh, in air actually. In air, even the fluid medium is very crucial, but I'm saying that it's in air. So what we are starting the course is, of course, how light behaves as this is light coming from this laser, how it behaves as it is in lenses, is incident on these mirrors, right, and how as it is incident on this polarizing beam splitter as well, how it passes, transmits, like reflects like this, given by the electric field, varies as have it incident dielectric media. So that is the first topic that we cover in this. Thing we had done was just the very which we kind of refreshed, but the first is going new. This is also something which most of you have done before in the second year class, but cover this first. Okay, so let us try writing. So this is basically an electromagnetic wave. Shit. EM wave at through dielectric is going to be really painstaking. I think what we can do for this class is mostly have actually you guys derive. Let me see. I'll draw the stuff and I'll maybe ask you to understand. Okay.
Sir, you can only draw the things. Other things you can just, like this text, you can just say it verbally.
That's tough, Ronak, because basically there are a lot of equations here. Let me see. We'll try to get, yeah, this is a disaster actually, not getting the stylus. Anyway, so what we have essentially is for medium, which is one is N1 and this part is N2. Okay, and so this is my normal. Okay, by the way, and I have, say, a light beam which is incident like that. Okay, so the first thing that I will ask you is what is, okay, so this is my theta I, the angle of incidence. There is something called the plane of incidence. Do you know it? Class, what is the plane of incidence? Anybody knows that? Yeah, what
The
is the plane of incidence defined as?
plane containing the angle of the line of incidence and the normal.
Line of incidence. Yeah, exactly. So it is essentially the incident ray. Okay, so it is the incident ray and the normal. That is the plane of incidence. So in this case, I'm actually plane of incidence is one, and the surface is actually something which is coming out of my screen. Okay, that is the surface. Okay. So essentially what I'm trying to look at is there is this beam coming in, and what happens at this interface is part of it gets reflected and part of transmitted, right? And of course, this is my angle of reflectance, which I know is the same, but which I still write as theta r, and this is theta t. Okay. So, what do you think are the intricacies of this problem? Let me first ask that. What are the interesting things about this problem? What that consider when we are dealing with this problem? What are the interesting aspects? What do you think that we have to keep in mind when we solve this? What happens? Please, let's discussion. Let's have a. I am, as you understand, I'm seriously constrained today in terms of writing. But as, so, what are the things that? So, this is my incident ray. This is a reflected ray. This is what do I need to consider? Actually,
The energy
yeah.
transmit,
Go
yeah,
on.
the energy transmitted and the reflected should be, the addition of those should be equal to
Yeah,
the
so there is
incident.
conservation of energy. Whatever comes in should be distributed. Oh, okay. You are assuming something here. What are you assuming?
That there is no
There is
loss
no
by
absorption.
heat.
Very nice. Very, very important. You are assuming there is absolutely no absorption. Very good. We neglect absorption. Writing that will be a disaster for me. Acha, can we write on Word or something? It's probably possible. No? Maybe Word or PowerPoint is better here, no? But again, writing equations is a disaster there. Anyway, so let us still try. So there is one initial condition, okay. However, I'm saying what other aspects of this problem that are there anything which make what are the what makes this problem intriguing? Is it intriguing again or is it trivial? Do you think it's a very simple trivial problem? What does the class think? You think that there is a lot of stuff in this problem, or do you think this is just too easy? What are the things
The
we have to consider?
polarization of the beams.
Absolutely crucial. Why is that important? We have to consider polarization. Why?
Because the dielectric media will respond to the EM wave. The media itself will get polarized as a response to the EM wave.
Uh, that
Sir,
is
because
correct, but
the polarization can be in the plane of incidence or outside the plane of incidence.
absolutely right. Absolutely right. the polarization. So I think one thing that needs to be highlighted to all of you is that we are not considering the medium response here at all. I mean, almost at all, in the sense that we're not really considering the dielectric constant. Why is this a dielectric medium? Is that it allows the beam to both transmit and reflect. Okay, that is the crucial thing that we are considering here. Okay, we are not really considering that this thing has bound electrons and they will respond to the input field and there will be a dipole moment, so there will be induced polarization, susceptibility, all that we are not considering. But as Anirudh said, the direction of the field is crucial. So the direction of the field can be in what aspect? It can be, as he said, it can be either in the plane of incidence perpendicular to the direction of K, either that, or it can be out of this, out of the plane. It is basically coming out of the plane of incidence, right? So in one case we call it S polarized light, and the other case we call it P polarized light, right? So S polarized is something that is out of plane and P polarized is in plane. Okay, that is crucial. So, but then, okay, so that means, by the way, so if I just say S and P for electric, there is also a very crucial thing for the magnetic as well. We have to keep that in mind as well, right? So that is the story is essentially keeping track of both electric and magnetic fields and writing down the boundary condition equations. That is what this whole thing is about, right? So by the way, what are the boundary conditions here? What do you think will be the crucial boundary conditions here? Yeah, what is the crucial boundary condition here? What do you think? So we have, so as they say, there is one field that is in the plane of incidence, which can be called also something like the tangential component of the field, something that is in plane, and there is also the normal component of the field. So if you have this kind of an interface where you have this kind of, the beam electric, by the way, this is something intriguing and which which I like you to keep in mind. That is, we are actually considering waves here. Okay, though I am sort of drawing a ray, the ray picture inherently does not take into account so much as the polarization, in the sense that when we talk of rays, uh, saying that there is a wave vector doesn't really make sense. I am sort of representing the wave in the form of a ray. I think that is what should be correct. Okay, that is the crucial thing. So essentially what we are going to write down, so as Anirudh said, we are going to vary the polarization. And what is the other very crucial thing that is going to matter in a big way? The polarization of the beam, and what else? Very crucial.
Angle of incidence.
Of course, yes. Let us write that down. Angle of incidence while I'm writing, and the other
Sir,
one.
excuse me. This is
Yeah,
Ronald. I think it would be better to use PowerPoint for today. You can easily write the text as well as the equations and draw the figure because it has a pen tool inbuilt in.
it's possible. Equations
Yeah,
one, I have equation editor, no?
yeah. Like writing that will be much like faster because it's already LaTeX enabled.
Let me try PowerPoint. Okay, let me try PowerPoint. Let's try PowerPoint.
And sir, can you switch off your camera?
Yeah, that also something somebody has. It's a bandwidth difficulty. Yeah. Switch off. Okay, can you see this, guys?
Yes, sir.
Electric field gain, electric. Crucial things, as I said, it's polarization. It's polarization. Okay. Have depolarization in plane. Okay, this is crucial. Acha. These things are, it doesn't take sort of this.
So you can press Shift Tab.
Shift tab, is it?
Yeah.
Shift. No, that will go. No, no, I want this 2 to come, right? This is the problem. This thing. See, this is.
Means
How do you get to
double
2?
inter,
So if I want to get, so wait, I think maybe.
double inter, double inter.
What double it? Ah, yeah, no, no, no. Yeah, maybe here. Please to take this. What it does. Anyway, let's forget. So angle of incidence is crucial. What else? Let me think. What else?
Change,
Huh?
change in phase.
Change
Change
in phase. You think that is important?
the refractive index of both the sides.
Yes. Crucial. Absolutely, absolutely crucial. The refractive index is absolutely crucial in the sense that it is going to tell you what happens if I have n1 greater than n2 or less than n2, right? That is the most important thing, one of the most crucial things in this case, right? That is absolutely crucial. And no, 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 I just want to rotate this format. Sorry, not this. Have this and have this. Yes. So this is essentially my stuff. Right. Just choose this whole thing. Just move this. Okay. This is what I have. Fantastic. Okay. So things that I have to put else is N1 and N2. Okay. So as I said, refractive index, magnitude, refractive indices, right? With respect to each other. That is completely crucial. So generally what happens when, yeah, so when you have N2 greater than N1, what are the interesting phenomena that you see? So, or rather, so suppose you have N1 greater than N2. What are the nice things that you see?
TIR.
Huh? Yeah, yeah,
Uh,
exactly.
TIR.
Very nice things happen. Okay, so now we are basically going to just write down those equations in terms of the boundary conditions of the E field and B field. This is what is going to be done. Okay. So as my question to you had been, what is the chief boundary condition that we are going to sort of go by here? What do you think is the main boundary condition? Yeah. So you, as I said, I will tangential component and normal component, right? So
So the
what
field should be continuous at the boundary.
which feed all both components of everything? Yeah.
Tangential component will remain unchanged, but the normal
Uh,
component will change by the
of what?
dielectric
Of what? So of
electric field. Electric field.
very good. And normal component of
Normal component will be changed by a factor that will depend on the n1 and n2 values.
so basically what we look at is the normal tangential component of the electric field remains continuous, and the so corresponding to that we have the tangential component of the electric so field or induction, so magnetic field or induction.
For electric field, the tangential component will remain continuous, and for magnetic field, the magnetic induction, the normal component will remain continuous.
Correct. So basic, and do you remember why that happens?
Yeah, it can be proved from the Gauss's theorem as well by considering a cylindrical
And
surface.
each remain continuous, and the normal components of B and B of B rather and B remain continuous. Okay, and I have something where I want you guys to look at. I found a sort of a nice website which describes this beautifully. So that is what I'm going to share with you. Yeah, so this is a nice website. It sort of explains this very nice. They actually follow Gauss's theorem. If you want, yeah, you can just, so this is very, I think I would really encourage all of you to just go to this site and one can actually look at this as well. Let me just share this with you as well. Yeah, let me just share this. 1 minute. Oh, I have to stop this anyway. Let me stop and go to this. So can you see this? Can you see this website?
Yes, sir.
Yeah. So this is very nice. So they just do the entire treatment and they finally come to this thing that this is the normal component, as you see, that is continuous. And this is again writing in terms of the H and the electric field, they find the longitudinal component, this tangential component field is continuous on the interface. Okay. So this is very important actually. The tangential components of the electric field are not responsible for any buildup of electrical charges. This is something that is, as conceptually, it's something very, very interesting. So this is maybe physically, you can actually appreciate that because I do not assume any kind of charge sort of build up across the interface, it is kind of essential that the tangential component, I mean, the consequence of the tangential component is that you electric field incoming affecting the incident the medium on which it is incident at all. And can you tell me why do you think this statement is being mentioned, that the tangential component for any buildup of electrical, why do you think they are saying this? Huh? What do you think is the reason? Why is this being said? What?
Sir, can you repeat? Your voice was lagging.
My question was this statement that is the tangential component cannot be responsible for any buildup of phase. So my question is why this statement? Why is this being said? Hey, this is not so guy. By the way, are you hearing me properly?
Sir, people can't hear you. Your voice is breaking down.
This is IZ network. Can you hear? Hello,
Yes, sir.
guys.
Now we can hear you.
Arey bhai, I am sitting at IZ. Yeah, what can I do? I can't do anything better. This is not my mobile does not have any signal. So my question was this statement that tangential components of the electric field are not responsible. I mean, this statement. How does it follow from here? Why does it follow?
So tangential means like into the plane, right?
Yeah, something that is not into, but it's along the plane.
Along the plane, yeah.
And basically, if I now I have to keep on sharing. So basically, you saw that, right? So you have the k vector, you have the field that is perpendicular to it in the plane, and there is the thing which is perpendicular to it out of plane, the p polarization and the s polarization. So what is being said is the tangential component is the one that is in plane. That is continuous, and you can derive this. Basically, by Gauss's theorem, they have derived it very nicely. But the statement is, as a result, this shows that there cannot be any charge accumulation due to the tangential component on the field, on the material, on the medium, at the interface. Why is this being said?
If there would be any static charge accumulation, it would be at the cost of the electric field itself.
Absolutely
But
right.
you can see that
Absolutely right. So, by the way, who is this guy?
yes.
So, who are you?
Sir, I am Chitradeep. I have joined SESI as a
Very
PhD
nice,
scholar.
very nice. So this is exactly correct. So basically what Chitradeep said was that if you have an electric charge development, obviously the electric field itself would change, right? So therefore it is contingent that this follows that. So one can also say that that follows this. But these are interlinked. If you have the tangential component continuous, then that cannot cause any electrical field because otherwise charge will lead to a change in the field itself. Okay, so please refer to this website in order to just brush up the concept about why this happens. Okay, Acha, so let me now shift back to the PowerPoint. Okay, so this is my essentially this is my incident light ray. This is my okay. This is my whole situation, right? Now, as I said, there will be two sort of conditions, right? One is I have the plane of polarization along out of plane. I have the plane of polarization in plane, right? So what I will do now is to consider each of these situations individually. Okay. So let us consider the condition for the electric field essentially to be S polarized or something that is coming out of the plane. Okay, so let me just draw this. the hell, man? What is they? No power thing, is it? I'm trying. Anyway, so what I'm trying to draw is the electric field out of plane, which means that I consider S polarization. Okay, so if this thing behaves well, I can do this, or else let me see. Oh man, this is all gone. Anyway. Behaved horribly. So representatively, we typically say that. What is happening? This is coming out of plane, and so let us just write this down, that we are going to have the electric field S polarized. Case 1, electric field S polarized. Okay. So this is coming out, right? And then I have my K, which is essentially in this direction, in the direction that you see, right? K, I say. Okay. So electric field EI, that is coming out of the plane. So can you tell me what the direction of the magnetic field will be? K is like that. Electric field is coming out here. Then the magnetic field will be in what direction?
So in the plane of incidence.
Correct. No, but which direction? Will it be like that or will it be like this?
Sir, the black circle means pointing toward
Pointing
outside.
outside. So this is the typical convention. This is going out of plane, coming outside. So my
So
question
it will
is,
be downwards.
Southwest.
Southwest.
Yeah.
sorry? No,
Uh,
I'm basically, my nomenclature is here is, so this thing, oh, you're saying that it's going in, no, but, so what I typically want to mean here is it's coming out of my computer screen.
yeah,
Okay.
so sir, we said the magnetic field should
Magnetic
be
field, okay, okay, what is southwest, right?
southwest.
Correct. Very good. Yes, indeed, correct. Do it this way, right? Is that fine? Everybody?
Yes, sir.
Do you agree? This is fine, right? Shape, outline, arrow at the end. Perfect. So magnetic field is this way. Perfectly correct. Let us just again draw this guy there. This thing is problematic. Great. And what about here? What about here? Which way will it be there?
Southeast.
Southeast. Perfect. Good. Arrange, rotate by. Perfect. And here, this is the same as here, right?
Sir, the electric field in the reflected part, shouldn't
Electric
it
field.
be inwards?
Huh? What? Come again?
The electric field in the reflected part, shouldn't it be inside the plane? Then the
Why?
magnetic, because it will.
Might see. No, but that cannot happen, right? I mean, how can the electric suddenly? It's always the incident is out of plane, right? So why will the thing be in plane suddenly? I mean, see, you are always considering. See, the my boundary condition is that the tangential component of the electric field is basically continuous, right? So that is the thing that I typically will always go by. So the it's always out of plane, right? So if it's out of plane in the incident direction, transmitted also it will remain out of plane, right? Why will it shift suddenly?
Sir, I'm talking about the reflected part.
Huh? Oh, this part.
Yes.
So why will it change? Why will it go down? It's like electric field, the normal component, why will it change, right? If it's coming across this, it will remain like this, right? Because that is why you're getting that magnetic field this way, isn't it? So,
Yeah.
right?
Direction of K changes, right? So it will
K
not
is
be
changing, obviously.
directed.
It is the K which is shifting because the K it's always what? Remember, it's K cross E, right? And that is something which you
Yes,
always
yes.
have to keep in mind, by the way. This is the crucial part. K cross E. K cross E is E. So this is essentially this is what we use to find the direction of E for a given E. This is always what we use, K cross E. So your K, incident K is this, your reflected K is this, and of course your transmitted K is just shifted in terms of angle. Right? Now we have the thetas also. And that will be a issue to write. Let me see. What is the Greek for theta is I think Q, right? Wait. So theta is your incident angle, theta I, the reflected angle is theta R, and the transmitted angle is theta E. Oh, shit, this is not tau. This is not symbol. So done. This is all my drawings finished. Done. Fantastic, right? So now what I want to write down is just the boundary conditions. What do you think will be the boundary conditions, by the way? As the boundary condition is clean, that the remember that the tangential component or components of E and H are continuous. So then obviously what you have is nothing but H, right? So here my B is in the plane. Acha, so very crucial. So if this is theta, what is the component of B which is, so okay, another very crucial thing. This is positive X, okay? This is negative X. I'm considering this is positive and that is negative. So if I have this angle is theta, I will obviously I have a bi cos theta and I have a bi sin theta, right? So what will be the component of the magnetic field of the incident part? The tangential component will be what? And by the way, I'm considering also, by the way, this is also important. I'm consider a a non-magnetic medium. That is very crucial. What does that mean, by the way? What does that mean? Log negative.
Mu equals to 1.
Yes, correct. Mu equals 1. So my question was, in case of the magnetic field in the incident direction, what should be the component? So basically the tangential, right? So do you want the component along? So this was your magnetic field, Bi, or this is Bi, that is my, what you consider is the component along the x direction, right? That is a tangential component along the interface. The component along the interface will be nothing but the cos of, if this angle is theta, then you can easily see that what is this angle? What is this angle? If this is theta, theta, right?
Theta.
Very obviously theta, right? So then, obviously, right? Because this is 90 minus theta, then that is 90 minus theta. This whole thing is 90, so this is theta. So that is it. Very simple. So I will and it is negative sign because that is the one that I have. This is Bi, that is minus Bi, right? So I will straight write down minus B. Mu is 1, right? So B is H. Okay. So minus Bi cos theta I. What about the reflected part? What is that? What will be that? Reflected part में क्या होगा?
BR cos theta I.
BR cos theta, and anyway we know that theta R is equal to theta I, right? And this one, the transmitted part, obviously, right?
BT cos theta.
Cos theta T. These are all symbols. I am not changing. I'll change them at the end. Okay. This is going to take too long otherwise. ये है oh, this thing is just suddenly getting crazy. Again, it stopped. There's a major network problem today. Came back. Okay, so remember, I want finally, okay guys, what is that I want? What I want to find out, I finally want to find ER by EI, right? That is what I want to find, the reflectance, which is nothing but the reflectance. And what else do I want to find? I want to find the transmittance, which is equal to E T by EI, right? So I have to get this in terms of the electric field. So how do I do that? What do I use to get this thing in terms of electric field? What will I use?
B equals to E by C.
Correct, right? So I have to use B equals E by C, which is also equal to, in this medium क्या होगा? C will be equal to C by V, right? So remember, C is nothing but V by C by V, right? It is not C actually. It is basically the velocity, right? So V is C divided by N, correct? So the moment I do that, what does this equation become? Minus EI by VI cos theta I plus ER by VR cos theta, cos theta I and cos equal and T by VT cos theta T. Right? Oh, I forgot the refractive. Whatever. So this I right now use the then what I essentially get is cos theta I. So by the way, you know that theta I is equal to theta R. So just tell me if I'm right. ER minus EI is minus of NT cos theta T dt. Is that correct? Can you check and tell me? Huh? Well, I change these things into thetas. ठीक है? Is that correct?
Yes, sir.
Correct, no? What will be the other? So I need another boundary condition, right? I have to get rid of, because I want to do ER by EI and ET by EI, I have to get rid of one of these. So what will be the other one in terms of electric field? What will I write? Electric field. Huh? Electric field क्या होगा?
EI plus
Is that
ER
clear
equals
to
to
everybody? Huh? Who said that? Vishwajit? So basically, we have to have EI plus ER equals ET. That has to happen, right? That is fine, isn't it?
Yes.
Then done. Now it's just very simple, right? So now what we have is, if you just replace these, what will we have? Finally, what do we have then? If I replace these things, Polo, can you tell me? So then Ni cos theta I. Yeah, I think I can just write this directly. It will become 2 Ni cos theta I equals Et cos I Ni cos theta T, right? Which basically means that I can just write down my two relations. Write down here. So essentially, I have T divided by EI as NT cos theta I Ni cos theta whole thing divided by twice Ni cos I. And can you tell me the ER by EI? ER by EI क्या होगा? On that? हाँ, क्या होगा? हाँ? What?
You have write down ET by EI.
Yeah,
ET by EI will be other
transmission,
way
right?
around. So that will be other way around. 2ni cos theta I by that thing, which are plus side, not minus.
उल्टा लिखा क्या? Just check that out. हाँ, ये उल्टा लिखा. Correct, you're right. You're right. ये आ गया है.
And that will be plus.
Plus.
Yes.
But what will the other one be? This one is, you should just, yeah, but this is very simply we can derive from here. No?
Just make the denominator negative, and then the same means numerator will become the
Denominator we cannot change.
denominator will remain the same, and make just previous term, put it in the numerator, that nt cos theta I plus minus ni cos theta t.
Is this correct, or should it be ni cos theta I and nt cos theta t? Just check this from here. These are my.
Ni cos.
I think this is wrong, no?
Ni cos theta I minus nt cos theta t.
Correct. This is wrong.
Yeah.
This is ni cos theta I.
That's still fine, sir. That's a plus sign.
No, but this is wrong, I think. No, it is ni cos theta I and nt cos theta
Ni
t.
nt.
Ni and nt, right?
Yes.
But what will be change from here? So I will. So er plus one. Basically, you have to put, instead of et, you put ei plus er. So you can directly see that this will become ni cos theta I will. So if I take ei, it will become nt cos ni cos theta I minus this thing, na?
Yes.
Yes.
Straight,
Minus
right?
nt cos theta.
Correct. So it will basically just ni cos theta I minus nt cos theta t. And this has to be, can you, why this has to be this?
Yes.
Why? This has to
2nt.
huh? Why?
That's
Kya? Why does this, what is this one we can, and at your level you should be able to predict this. What is the main takeaway of this?
Because the reflectance and transmittance should add up to 1
That
uniform.
is of course there, yes. Okay, let me just write down from here. So what is the main takeaway from here? Let us see. What are the main takeaways? Main takeaways. What happens when you have ni smaller than nt?
Negative, it becomes negative.
and
If ni is smaller than nt, this thing, so obviously, so ni less than nt means, essentially means what? Theta I greater than theta t, right? Obviously, because from the refractive index Snell's law, you know that. है ना? Which obviously means that cos theta I, which means cos theta I is less than cos theta t. So this I can say is this ER. So if I say this as TP, T for T parallel, I want it small, and I call this as RP. So RP is negative. What is this meaning? What does this mean, guys? What is the meaning of RP being negative? इसका मतलब क्या हुआ? RP is negative means what?
So pi phase difference.
The pi phase difference which comes when I get reflectance from a rarer medium to a denser medium. Okay, and how will you find this out? How can you determine this? By the way, let me ask this very, very crucial question. When you do an experiment, do you actually measure TP and RP?
No, the square
No.
of it.
Square of it. So how will you be able to prove this? How will you be able to prove this? That this is happening? In an experiment, if you take a square, तो gone. This thing is gone. How do you? Okay, so let me. The other takeaway obviously is that Ni greater than Nt means Rp is positive. How do you prove
Sir,
this?
you put a polarizer.
Polarizer say how will you measure? Okay, tell me. Polarizer say how will you measure?
So if the polarizer is crossed with the electric field, then we won't get any output.
No,
Yeah.
someone gave
Oh,
right answer in the
Rohan,
chat.
I'm not asking that. Rohan, what I'm asking is how do you prove that RP is negative?
Oh.
I am asking the class what is the meaning of RP is negative. I am not asking about polarizer. The question is the question clear to all? What is the meaning of RP being negative?
Yes, the question is clear.
Bolo answer bolo abhi. If you don't, I will not answer this. Period.
Uh,
If you
sir,
cannot give me the answer now, that is homework for next class. Bolo.
if there is a possibility, if we could
So the
interfere the transmitted wave with the initial wave, we should not get any interference because it will be out
okay.
of
So who is
some.
this piano? Who is
Yeah.
this? Anyway, so piano is clever. So anyway, the question very important part of the why is the question interesting is that acha, let me just write the point is you cannot measure RP or TP in experiment. This is extremely important. In fact, let me create a next slide for that. How do you prove that there is a phase change when reflecting a beam from rarer to denser media? Yes, will not come out through intensity experiments. Is that clear? Will not come out in intensity experiments because so this essentially means experiment. Let me just find out. No, let me just go from here. The first point is crucial that RP seems to have a phase change of pi when N1 is Ni is less than Nt, right? Will not come out to intensity. The only way is, as Priyanut said, interference experiments. And what interference experiment have you seen this very as a very critical part of? Which experiment was this a very critical part? Huh? What third year sub chup kya? Which was the experiment where this is manifested beautifully? Where phase change of pi while reflecting from rarer to denser media?
Newton's ring.
Newton's ring. Oh man, no, not at all.
Michelson.
ring.
Michelson,
Maxender.
no.
Maxender.
Sorry,
Mach-Zehnder.
Arey Baba, very disappointing, guys. I think most of you did Mark Zehnder, no? All of you did. I think most of you, 80% did Mark Zehnder. In 2 months, you have completely forgotten. Critical aspect of Mark Zehnder interferometer. Shall we do that in class? You want somebody, I don't know, maybe for people who have, let me give that as an assignment. Okay. So I will give you the, let me just give you the thing. Oh, okay, let me give this as an assignment. I think that is nice. Just give me 1 second. Let me just give this as an assignment. I'll just give you the setup and I will just ask you to explain. This is the setup of Mach-Zehnder. This is the light source. Okay. This is the beam splitter 1. This is a beam splitter. This is a mirror. That is a mirror. Beam comes here, goes there, gets split. Basically gets split between this beam splitter. Goes to this mirror. Part of it goes to this mirror. Part of it goes to that mirror. Gets reflected. Goes here. Once again, this gets reflected, this one gets transmitted. However, you also get a reflection of this beam out here and transmitting a transmittance of this guy here. The questions to the class is, what will fringes look like in, or what will be the difference between fringes at 1 and 2 detected, that is 1 and 2. Okay, given that the experiment is being done in a normal lab, the beam is propagating in air. Okay, this is something which the class has to tell me, and consider this, and I think this is very easy. I want this to be uploaded as an assignment tomorrow itself. This is just very simple. This is just you have to basically explain. Okay, next part. You can see that this beam splitter. Okay, let me just write down the beam splitter names. This is BS1, that is BS2. So importantly, the dark portion of BS1 and 2 are the coated sides. Matlab, the the reflection, basically the reflections, the BS1 and BS2 are being treated. That is important. So BS corresponds to beam splitter, not some other thing that creative minds might think. BS is beam splitter, and the dark portions are coated sides. These are beam splitter 50-50. Okay, 50-50 are the coated sides. The reflections predominantly happen from those sides. My question is, will the result remain the same if the BS are flipped by pi? You understand? So here I have the coated side facing the beam, I flip it so that the uncoated side faces the beam. And is that important at all? You understand? Is this clear to everybody? Please tell me if it's not clear. This part is the coated side of the beam splitter. I flip it. I now have the uncoated side facing this light, right? And I can, as you can understand, I can have 4 combinations, right? I can have coated sides facing here. I can have coated sides facing here. I can flip this 2 combinations. I can flip this at the same thing here. I get 4 total combinations. My answer is, what you get at this 1 and 2, will that remain the same? Okay, is that understood? So please upload the results by just one document. Answers to basically question 1 and 3. And you have to, of course, show me why. Why? And quantitatively. Answer quantitatively. I mean, not just quantitatively. Okay, let me just ask this. The medium, the BS has a refractive index of 1.516. I dip the whole apparatus in a fluid of Ri 1.526. What will happen? And what will happen, Mani? You have to answer everything. What will happen, Mane? You have to answer every possibility that you think is important. And we will discuss it tomorrow. Is that clear? By tomorrow, this is something which you can finish in half an hour, not even that. Is that clear? We'll end today. Any questions?
Sir, will
Sir,
you
one thing.
open a portal on VLearn that we have to submit, or we have to mail it?
Yeah, I think it's better. I'll open a portal on VLearn. I am switching on my camera for some time. Okay. So yeah. So any questions? I'll open a thing for assignments. Yeah. So assignment 1 immediately I'll submission date 2. Abhi I'll put immediately. I'll put. Okay. No questions then, na? Please. See.
Sir, tell them to check the calculations by themselves.
See, guys, I mean, if you are going to cheat, you're going to copy, I can't help it here. I mean, if you copy, I can't help it. But please, I mean, you guys are fourth,
No,
fifth.
the calculation you have done.
Of course, that is understood. See, I have jump steps. Please, I have jump steps. So, of course, yeah, if I could write, it's better. Typing is pain, right?
Yes,
So
that's right.
please check everything that I have done, and please check whatever I do in the future. I am very, very prone to, you guys know that, right? I have told you, I make silly mistakes all the time, and I want the class to be awake, not sleeping. Okay? Okay, so then tomorrow we meet, and let me stop the recording. And I sent you the mail. Everybody got the email, right? That the one link, I'm going to delete all the those messages, those class links. Those meetings I'm going to cancel. All the things I'm canceling. If some of you can somehow show me how that link that is given in classroom can be sent to transferred to Google Calendar without that link getting updated all the time, please tell me. Otherwise, consider I will delete all those meeting requests. Okay? Okay. Tomorrow. Bye.